Hello everyone. So in today's class, we will take up few tutorial problems on stability and Routh Hurwitz criterion. So in the class, we have discussed what is stability. What is stability, or when do you say a system is stable? A system is said to be stable if the inverse response of the system decays to zero as time tends to infinity. If the inverse response grows without bound as time tends to infinity, the system is said to be unstable. And if the inverse response neither increases nor decreases, remains a constant or a continuously oscillating, then we say the system is marginally stable or limitedly stable or neutrally stable. Okay, then we also saw what is BIBO, BIBO definition of stability. A system is said to be BIBO stable if every bounded input yields a bounded output. And a system is said to be BIBO unstable if any bounded input yields unbounded output. Okay, what do you mean by unbounded? It means it goes without any limit, any bound. Okay, and a marginally stable system or a limitedly stable system is one which whose output will be bounded for some bounded inputs and its output will be unbounded for some other bounded inputs. Okay, and we had also seen that stability is related with the location of the closed loop poles. If all the poles are in the left half of the S-plane, the system is stable. If any one of the poles is in the right half, the system is unstable. And if you have unrepeated roots on the imaginary axis, then the system is marginally stable. If you have repeated roots on the imaginary axis, system is unstable. Okay, and then we had also discussed what is Routh Hurwitz criterion, which states that the number of sign changes in the first column of the Routh array will tell you how many roots lie in the right half of the S-plane, making the closed loop system unstable. Okay, let us take some examples. So you are given with a characteristic equation like this. We are given a characteristic equation like this. Okay, S cube plus 6s square plus 12s plus 8 equal to 0. We need to check whether the closed loop system is stable or not. Okay, what we are given is the characteristic equation. If you factorize the characteristic equation, you will get the closed loop poles. Okay, so we are going to check whether the closed loop system whose characteristic equation is s cube plus 6s square plus 12s plus 8 equal to 0 is stable or not using a Routh table. So what's the procedure? We have to create a Routh table starting from highest power of s cube, s square, s raised to 1, s raised to 0. How will you make the entries? Alternate elements 1, 12, 1, 12. All missing elements will be the second row 6, 8. What will be the next row? 6 into 12, 72 minus 8 whole divided by 6. That will be 64 by 6. There is no element here to enter, okay, because there are no more finite elements here. So obviously it will be 0 here. Okay, if you want, you can add a 0. Even otherwise also it is fine. Okay, what will be the next thing? 64 by 6 into 8 minus 6 into 0 whole divided by 64 by 6. That means 8. So is there any sign change in the first column? This is the first column, right? Do we have any sign changes there? No sign change. Okay, there are no sign changes in the first column. There are no sign changes in the first column of the Routh table. In the first column of Routh array. Hence, the closed loop system is stable. Hence, the closed loop system is stable. Okay, the number of sign changes in the first column will tell you how many roots lie in the right half of the S-plane, making the closed loop system unstable. So here, all the elements in the first column are positive. That means there are no sign changes. Hence, all the closed loop poles lie in the left half, and hence the closed loop system is stable. Let us try another example. S cube plus 3s square plus 3s plus 1 plus k equal to 0. Okay, we need to determine the range of k for stability. Determine the range of k for stability. Okay. Again, what will you do? As before, we start off with root table. Okay. So s cube, s square, s raised to 1, s raised to 0. So what will be the first entry? 1 space 3. What is the second entry? 3 space 1 plus k. What will be the next entry? 9. This into this. 9 minus 1 into 1 plus k. That means 8 minus k divided by 3. Okay. What will be the next entry? 8 minus k by 3 into 1 plus k minus 3 into 0. 0 whole divided by this thing. That means 1 plus k. Okay. Now you see, for sign change, for stability, there should be no sign change in the first column. For stability, there should be no sign change. There should be no sign change in the first column. Okay. So 1 is positive, 3 is positive. So 8 minus k by 3 should also be positive. Therefore, condition number 1, 8 minus k by 3 must be greater than 0, from which k should be less than 8. Okay. How will you find this? You take the extreme case, that means you equate it to 0 to find the limiting case or the extreme case. Okay. So we'll get 8 minus k equal to 0, or k should be less than 8. That's the condition. Okay, from s raised to 1 row. Now also 1 plus k should be greater than 0. K plus 1 should be greater than 0, or k should be greater than minus 1. Okay. So this is the range in which k has to lie so that the system becomes closed loop state. Okay. So that means if you combine these two, you will get minus 1 less than k less than 8 for closed loop stability. For closed loop stability. Okay. Let us take another example. 3. S raised to 5 plus s raised to 4 plus 4s cube plus 4s square plus 2s plus 1 equal to 0. Okay, we have to check whether the system is stable or not. So we'll start off with our root table. S raised to 5, s raised to 4, s cube, s square, s raised to 1, s raised to 0. What will be the first row? 1, 4, 2. 1, 4, 2. What will be the remaining row? 1, 4, 1. 1, 4, 1. What will be this entry? 1 into 4, 4 minus 1 into 4, 4. 4 minus 4, 0 divided by 1, 0. But the next thing, 1 into 2, 2 minus 1 divided by 1. That means 1. So here we have come across the case where the first element in a row is 0. So how to solve this? There are two methods. I will tell one by one what the methods are. Okay. So first one is you replace this 0 with a small number epsilon. Okay. You replace this number 0 with a small number epsilon. Then, so now you see what's the row here? Now S cube row is epsilon space 1. So now you can create the remaining part of the table. What is the next row? 4 epsilon minus 1 by epsilon. 4 epsilon minus 1 by epsilon. Okay. So then what will be the next entry here? So this into this minus epsilon to 0, 0 divided by this thing. That means 1. What will be the next entry? This into this minus epsilon divided by this. So if you do that, you will get. So what is the operation? Operation is like this. 4 epsilon minus 1 by epsilon into 1 minus epsilon into 1 whole divided by 4 epsilon minus 1 by epsilon. So if you simplify that, you will get minus epsilon square plus 4 epsilon minus 1, okay, divided by 4 epsilon minus 1. What will the next entry? This into 1 minus this into 0 divided by this. That means 1. Now what you have to do? You tend epsilon to a small positive number or negative number. You can do either way. Both will give you the correct answer. Okay. So let me take epsilon to be a very small positive number. Say epsilon is equal to 0.01. Okay. So you see 1 is positive, 1 is positive. So epsilon being equal to 0.01. Assume epsilon is 0.01. That's also positive. What about the next entry? This 4 epsilon minus 1 by epsilon can be written as 4 minus 1 by epsilon. And when epsilon is 0.01, what will be effectively what happens? This number becomes negative. So how many sign change? One sign change. Okay, we have one sign change like this. Okay, then what happens? Here you see you substitute epsilon equal to 0.01. Again, it remains negative. This number effectively remains negative. So negative, and then we have a positive one. So again, another minus 2 plus another sign change. So in total, we have 2 sign changes. What do you mean by that? It means that out of the 5 positive poles, 2 poles lie in the right half and the remaining 3 are in the left half of the S-plane. There are 2 sign changes. There are 2 sign changes in the first column. Hence, 2 positive poles are in right half S-plane. Right half S-plane. So what's the conclusion? Closed loop system is unstable. Therefore, closed loop system is unstable. Closed loop system is unstable. Okay. Now there's another alternate method. When you come across a row whose only first entry is 0, what you can do is you replace S with, say, 1 by P, where P is a variable in the entire CAPS equation. Okay. So what will you get? 1 by S, 1 by P raised to 5 plus 1 by P raised to 4 plus 4 by P cube, 4 by P cube plus 4 by P square plus 2 by P plus 1 equal to 0. Okay, so take the LCM and see what you are getting. So what do you get? What do you get? So this means, this implies what? So the polynomial will be what? When you take, let's say, you will get P raised to 5 plus 2P raised to 4 plus 4P cube plus 4P square plus P plus 1 equal to 0. Okay, just take the LCM and simplify that. Okay, now the table will be in terms of P. Okay, so P raised to 5, P raised to 4, P cube, P square, P raised to 1, P raised to 0. What is the first row? 1, 4, 1. 1, 4, 1. What is the next row? 2, 4. Okay, 2, 2, 2, 4, 1. 2, 4, 1. What is the next entry? 2 into 4, 8 minus 1 into 4, 4. Divide by 2. That means 2. What is the next thing? 2 into 1, 2 minus 1 into 1, 1. 1 by 2. That means 0.5. What is the next entry? 2 into 4, 8 minus 1 divided by 2. That means 3.5. Okay. 2 into 1, 2 minus 0 divided by 2. That means 1. What is the next thing? 3.5 into 0.5 minus 2 into 1 whole divided by 3.5. So we will get minus 1 by 14. Okay. What is the next entry? Next entry will be this into this minus this into 0 divided by this. That means 1. So how many sign changes are there in the first column of the root table? How many sign changes? Plus 2 minus 1 sign change, minus 2 plus second sign change. So there are 2 sign changes in the first column of the root array. Okay, 2 sign changes in the first column of the root array. Therefore, the closed loop system is unstable. Got it? Let's try another problem. S raised to 6 plus 2s raised to 5 plus 8s raised to 4 plus 12s cube plus 20s square plus 16s plus 16 equal to 0. Okay. So again, we will start with the root table. So s raised to 6, s raised to 5, s raised to 4, s cube, s square, s raised to 1, and finally s raised to 0. What is the first row? 1, 8, 20, 16. 1, 8, 20, 16. What is the remaining? What is the next row? 2, 12, 16. 2, 12, 16. Okay. So you can see that in the S raised to 5th row, there's a common factor 2. Okay, so if you want, you can divide throughout with 2. Okay, so you will get 1, 6, 8. Okay, we have divided the coefficients of the s raised to 5th row with the common factor 2. So we got 1, 6, 8. What is the next thing? 1 into 8, 8 minus 1 to 6, 2 divided by 1. That means 2. Then 2 into 20, 40 minus 16, 32 divided by 2. That means 2 into 20, 40. 40 minus 16 is 30. 40 minus 16 is 12. Sorry, then 40 minus 16. 24. Okay, so 24 by 2, 12. Then what is the next thing? 2 into 16, 32 minus 1 into 0, 0 divided by 2. That means again 16. Okay, so again we have here a common factor of 2. I can write 1, 6, 8. What will be the next row? 1 into 6, 6 minus 1 into 6, 0 divided by 1, 0. Then 1 into 8 minus 1 into 8 by 1, again 0. Okay, so that means we have come across a case where all elements in the row are 0. So whenever you come across a case where all elements in a row are 0, it means that there are roots symmetrically located about the origin of the S-plane. Okay, for example, maybe like this. Okay, it is symmetric about the origin, or it may be like this. Still, it will be symmetric. Oh, this is a mistake in drawing. Still symmetric about the origin of the S-plane, or a combination of this thing, or it may be something like this. Okay, still symmetry about the origin of the S-plane is maintained. Okay, so normally you will get an odd row full of zeros. Okay, see here, it was S cube row that became full of zeros. Okay, so in this case, how to solve this? We have to form auxiliary polynomial. What is auxiliary polynomial? It is an even polynomial constituted out of the rows immediately above the 0 row. What is that? It is this s raised to 4th row. So what will be our auxiliary polynomial? Our auxiliary polynomial will be what? S raised to 4 plus 6s square plus 8. This will be the auxiliary polynomial. Okay. So why it is called an even polynomial? Because the coefficients of s in that auxiliary polynomial will be always even. S raised to 0, s square, s raised to 4, and so on. Okay. So we have to first formulate auxiliary polynomial, differentiate that d by ds of a. What will you get? 4s cube plus 12s. Okay. So now you replace this 0 row with coefficients of the derivative of the auxiliary polynomial. So I can write this as 4 and 12. So again, there's a common factor of 4 here. So I can write this as 1 and this as 3. Okay. Now what will be the next row? 1 into 6. 6 minus 1 to 3. 3 divided by 1. So it will be 3. What will be the next one? 1 into 8. 8. What will be this thing? 1 into 8. 8 minus 0 divided by 1. That means 8. Okay. Then what will be the next thing? 3 into 1. 3 into 3. 9 minus 8 by 3. That means 1 by 3. And lastly, it will be 8. Okay. So do we have any sign change here in the first column? No. All the elements are positive. Okay. All the elements are positive. So what's the conclusion? System is stable? No, you cannot say that. Okay. See, as I told you before, since we got one row full of zeros, there can be a case like this with a pair of poles on the imaginary axis, unrepeated roots on the imaginary axis. That means if that's the case, system is marginally stable. Okay. So whenever you have a row full of zeros, you factorize your polynomial actually, the characteristic polynomial, to make sure that whether it is marginally stable or whether there are repeated roots on the imaginary axis. Okay. Routh Hurwitz criterion will tell whether system is stable or not. It will not say whether it is marginally stable or if there are repeated roots on the imaginary axis. That it will not say. Okay. So to be precise, you factor system. So you see this auxiliary polynomial s raised to 4 plus 6s square plus 8 must be a factor of this polynomial, this thing, s raised to 6 plus this, the original characteristic equation. So first let us factor this thing. So our auxiliary polynomial was What are we now doing? We are now trying to factorize the characteristic polynomial to make sure to know whether the system is actually stable or whether it is marginally stable or not. Okay, that's our aim. So for that, we have to factorize this thing. So what's the auxiliary polynomial? S raised to 4 plus 6s square plus 8. Okay, how will you solve this? Equal to 0. Yes, yes. How will you solve this? You put s square equal to x. So what will you get? You will get x square plus 6x plus 8 equal to 0. If you factorize this, what will you get? X is equal to, that's the equation, quadratic equation. Okay, so what will you get? X is equal to minus 4 and minus 2. But what is s? What is x? It is s square. So you will get s as plus minus j2 and plus minus j root 2. Okay, so this is the case. Sigma j omega. There is a j2 here. There is a minus j2 here. There is a root 2, j root 2 here. There is a minus j root 2 here. So what can you conclude about stability? System is marginally stable. Okay, system is not stable. System is marginally stable. Since unrepeated roots are on the imaginary axis, the closed loop system is marginally stable. The closed loop system is marginally stable. Okay, so this gives us 4 roots. What is the order of the characteristic equation? Sixth order. It's of the order 6. That means there are 2 more roots. How will you find that? You divide this original polynomial with the auxiliary polynomial. Okay, so how will you do that? You divide that. S raised to 6 plus 2s raised to 5 plus 8s raised to 4 plus 12s cube plus 20s square plus 16s plus 16. You divide that with the auxiliary polynomial. Okay, auxiliary polynomial was s raised to 4 plus 6s square plus 8. Okay, how will you solve this? S square. So you get s raised to 6 plus 6s raised to 4 plus 8s square. Okay, subtract. What will you get? 2s raised to 5 plus 2s raised to 4 plus 12s cube plus 12s square plus 16s plus 16. Okay, now what next is 2s raised to 5. So you multiply this polynomial with 2s. So what will you get? 2s raised to 5 plus 2s raised to 4 plus 12s cube. Oh, sorry. 2s raised to 5 plus 12s square, 12s cube plus 16s. 16s. Okay, so subtract. What will you get? 2s raised to 4 plus 12s square plus 16. So that means this will be plus 2. So the remaining factor of the original characteristic polynomial is s square plus 2s plus 2. So if you factorize that s square plus 2s plus 2 equal to 0, you will get your s as minus 1 plus minus j. Okay, so where are the closed loop poles? Closed loop poles are at s is equal to minus 1 plus minus j plus minus j2 and plus minus j root 2. Okay, so system is not stable, system is marginally stable. Okay, so whenever you come across a row full of zeros, make sure that you factorize the polynomial and where the actual closed loop poles are. Otherwise, you are bound to make wrong conclusions regarding stability. Okay, let us try another problem. Find the values of k and t. Q. Find the values of k and t such that all roads will have real parts more negative than minus 2 for t square plus s plus k equal to 0. Okay, find the values of k and t such that all the roots will have real parts more negative than -2 for t square plus s plus k equal to 0. Okay, so keep in mind when you are doing Routh Hurwitz criterion, we are just checking stability about the imaginary axis or about the imaginary axis of the S plane. Okay, so what is sigma here? Sigma is equal to 0, 0, 0. Okay, about this axis where x is equal to 0, or sigma is equal to 0. Okay, but here what's the question? We are asked to find whether roots are more negative than -2. That means you need to shift the y-axis to -2 point. Okay, so basically we have to shift this axis to -2. Okay, so this is my new coordinate now. This was j omega. So this is j omega n, new omega. Okay, it has been shifted by 2 units to the left half of the S plane, right? So that means what? I will define a new variable, say s new as s plus 2, because it has been shifted to the left by 2 units. So what is s from here? S will be equal to Sn minus 2. Okay, now you replace this s in this Cap's equation with Sn minus 2. Okay, therefore t square plus s plus k equal to 0 will become what? T into Sn minus 2 whole square plus Sn minus 2 plus k equal to 0. Okay, simplify this. What do you get? T into Sn square minus 2 Sn plus 4 plus Sn minus 2 plus k equal to 0. So that means t Sn square minus 2t Sn plus 4t plus Sn minus 2 plus k equal to 0. Okay, so t Sn square, then or I can write Sn square into t, okay, plus Sn into what? 1 minus 2t, okay, Sn into 1. Did I make a mistake here? 40. This becomes 40. Okay. Minus 4Sn here. It's 4Sn. Okay, when you expand this thing, S square minus 4Sn plus 4. Okay. So you will get Tsn square minus 4 Tsn plus 40. Okay. So it becomes 1 minus 40. Sn into 1 minus 40. Okay. Plus 40 plus k minus 2 equal to 0. Okay, so our aim is to find k and t. So now you see, if there are no sign changes in the new plane which has been shifted to the left by 2 units, then we can be definite that all the roots have real parts more negative than -2. Okay, so we will now do the root array. So it starts from Sn square Sn raised to 0. Okay, t 4t plus k minus 2. Okay, what will be the next thing? 1 minus 40. What will be the next thing? This into this minus this into 0 divided by this. That means 4t plus k minus 2. Okay, so what's the condition 1? T should be greater than 0. What is condition 2? 1 minus 4t greater than 0. So 1 minus 40 greater than 0 means what? T should be less than 1 by 4. Okay, so t should be greater than 0 and t should be less than 1 by 4. That is the condition for t. Okay, therefore, t should lie between 0 and 1 by 4. Okay, now coming to the third equation. What is that? 4t plus k minus 2 should be greater than 0. Or what should be k? K should be greater than 2 minus 4. Okay, so these are the two conditions. So that system will have roots more negative than -2. Okay, I hope it is clear to all. So we'll stop here for the day, and so we'll stop here for the day and meet in a new class with a new lesson. Thank you.